Hello friends, welcome to evigyan. In the previous video, we talked about what physics really is. Today, we take our first technical step into the journey of physics, and that step is very important because before we talk about work, energy, force or motion, we must learn how to measure things. Today's topic is unit and dimension of physical quantities. Whenever we measure something, we are actually comparing it with a standard. For example, how long is a table? How heavy is an object? How much time does an event take? To answer these questions, we need units. A unit is a standard way of measuring a physical quantity. Without units, numbers alone don't mean anything. Why units matter? If I say the length of a table is 5, the first question you will ask is 5 what? Meters, centimeters or feet? Units make measurements clear and meaningful. They allow scientists everywhere to understand each other. Over time, different systems of units were developed. The two most common ones are the SI system and the British system. In the SI system, length is measured in meter, mass is measured in kilogram, and time is measured in second. From these, we get derived units like Newton, Joule, and watt. While in the British system, length is measured in foot, mass is measured in pound, and time is measured in second. The SI system was officially adopted in 1960. It is based on 7 fundamental quantities which are enough to describe the physical world. They are the meter, kilogram, second, ampere, Kelvin, mole and candela. Meter is the base unit for length. Kilogram is the base unit for mass. Second is the base unit for time. Ampere is the unit for electric current. Kelvin is the unit for temperature. Mole is the unit for the amount of substance. And candela is the unit for luminous intensity. What are derived physical quantities and derived units? Derived physical quantities are physical measurements that are defined in terms of one or more fundamental physical quantities. We have just discussed the 7 fundamental physical quantities. Those are length, mass, time, electric current, temperature, amount of substance, and luminous intensity. So fundamental physical quantities are the building blocks of all other physical measurements, while derived physical quantities are built on top of these building blocks. Let's see some examples of derived physical quantities. First example is velocity. It is a derived physical quantity whose SI unit is meter per second. Since velocity equals displacement divided by time, and in SI units displacement is measured in meters and time is measured in second, so the SI unit of velocity is meter per second, right? The second example we can take is acceleration. As we know, acceleration equals velocity divided by time. So the SI unit of acceleration is meters per second squared. Third example you can take is force. As we know, force equals mass time acceleration. So its SI unit is kilogram meters per second squared, which is also known as Newton. So these are few examples of derived physical quantities. Other examples are energy, power, pressure, and so on. Now it's time to solve some numerical based questions on this concept. Question number 1. The SI and CGS units of energy are Joule and Erg respectively. How many ergs are equal to 1 Joule? This is a question about the conversion of units. As you know, in the CGS unit, length is measured in centimeter, mass is measured in gram, and time is measured in second. So let's change kilogram to grams and meters to centimeters. 1 joule equals 1 Newton meter, which equals 1 kilogram meter squared per second squared, which equals 1000 times 10 squared grams centimeters squared per second squared, which equals 10 to the power of 5 ergs. Therefore, 1 joule equals 10 to the power of 5 ergs. The second question is, Mary drives 10 kilometers from her college to home in minutes. Calculate Mary's average speed in kilometers per hour and in meters per second. Here first we calculate the average speed using the given units. Then we can get the average speed into the desired units by picking the correct conversion factor and multiplying by it. The correct converging factor is the one that cancels the unwanted units and leaves the desired units in its place. Solution for part A. Average speed is the total distance traveled divided by the time of travel. So here average speed equals distance divided by time, and which equals 10 kilometers divided by 20 minutes, which equals 0.5 kilometers per minute. Now we want to convert kilometers per minute to kilometers per hour. For this we need to multiply it by the conversion factor, and that will cancel minutes and leaves hours. Since 1 hour equals 60 minutes, so the conversion factor is 60 minutes per hour. Thus average speed equals 0.5 kilometers per minute times 60 minutes per hour, which equals 30 kilometers per hour. Now let's solve part B. We have average speed equals 0.5 kilometers per minute. In this part, we want to convert kilometers per minute to meters per second. For this, we need to multiply it by a suitable conversion factor. Since 1 kilometer equals 1000 meters and 1 minute equals 60 seconds, therefore average speed equals 0.5 kilometers per minute times 1000 meters per kilometer times 1 minute per 60 seconds, which equals 8.33 meters per second. Unit may look simple, but they are the foundation of all physics. In the next video, we will talk about dimensions and dimensional analysis. Until then, stay curious, keep observing nature and keep learning physics. See you in the next video on evigyan.